Yeah. Okay. So we are discussing Hilbert spaces, and like if you have finitely many Hilbert spaces H1 up to Hn, then we can form this Hilbert space, which is the tensor product of these Hilbert spaces. So this is such a Hilbert space exists, and I mean, see all these Hilbert, when you are dealing with infinite dimensional Hilbert space, infinite dimensional separable Hilbert space, that's what you will deal with. So if it's not finite dimensional, if it is separable and infinite dimensional, all Hilbert spaces are same, and there is a unitary between them. There is no difference. But it is like what kind of avatar it is. I mean, it is what kind of properties it has. Okay, those properties should be preserved. Later, we will deal with some symmetric tensor product, Fock space, all that. They are all same in the sense. I mean, if you once you know it's separable. So when you do the tensor product, you are going to get separable Hilbert space that we are going to prove now. So if you take tensor product separable Hilbert space, you will get separable. You will get a separable Hilbert space. So there is no difference actually in the property of the Hilbert space. But then there are some particular vectors, particular thing we are dealing with. Using that, we will define operators and all that. So those vectors that will be preserved up to unitary. That's what we mean. So this tensor product we can form. In finite dimensional, they are different. If we have H1, which is of n dimension, H2 of m dimension, then the Hilbert space H1 tensor H2 is nm dimension, which is a completely different vector space, different vector space. But infinite dimensional, they are actually same. They have the same dimension because countable direct product of two countable set is countable. It's like that. Okay. So that's what the orthonormal basis will be. If you have an orthonormal basis, then if you take the direct product, that will be the orthonormal basis for the tensor product. So there is no actual difference in the as a Hilbert space. It's up to isomorphism. It's the same Hilbert space, but there is a unitary. I mean, here there is a unitary which takes the elementary tensor. So this is what is this Hilbert tensor product? By tensor product, we mean we can form what are called elementary tensors. Those elementary tensors, if you take the linear span and take the closure, that will be this. That will be the everything in the Hilbert space. That will be the complete whole of Hilbert space. So that is this property. There will be a unity. If you have two, see this Hilbert space is also defined through some process which is up to unitary. You can have another Hilbert space, then there is a unitary, but that will take this elementary tensor to elementary tensors. So that is what is being, it's not some arbitrary unitary. It is some which takes the elementary tensor to elementary tensor. So in a sense, this, but then we do something which for H1 up to Hn, we can take H1 tensor H2 and then take H1 tensor H2 and then take H3. We can do it in two ways. So this tensor product is associative. That's what I want to mention. Associative. That is, if you take H1, you can tensor with H2. So that gives a Hilbert space. Then you can tensor with H3. Okay? That is another Hilbert space. Okay. Now you can instead, we have already know using that kernel, we can already know this H1 tensor, H2 tensor, H3. We can directly do this. Okay? That's also we can do. Just to take the, you take this Hilbert space as a set, all these three Hilbert spaces as a set, then you take the direct product, define a positive kernel on that. Okay. Then the positive kernel, using that construction, whatever we have had the construction, using that construction, we get a Hilbert space. And that Hilbert space is the three tensor, H1 tensor, H2 tensor, H3. That is one thing. Or you can do H1 tensor, H2, which is you can take two at a time. Then another H3 you can do. Or you can do, so this will, there will be, so there will, these two has the unitary, you can take, then you can take H1 tensor, H2. This is the elementary tensor. Notice that this is not same element like them. This is just a notation. You have the direct, you have this kind of element in the direct product, X1, X2. You can include that set into this using that Gelfand transform. And that this is what is denoted by this. Okay. Similarly, you have other notations. So this X1 tensor X2, tensor X3, you can take it directly to this. This is a different element, okay, in this, right? And you call this unitary as U1, 2, 3. U1, 2, comma 3. 1, 2 is together and 3 is comma after 3. Then 3 after the comma. Similarly, you can do the same thing with H1 tensor H2 tensor H3. 2 H1 again H1 tensor H2 tensor H3. Here you can take any X1 tensor. I mean, so how is this unitary defined? This unitary is defined on this total set. And you can check that preserves the inner product, and that is how it is extended, right? I mean, this is just the definition is just on the total set. Total set means a set whose linear span closure is everything. Okay, you take the linear span. So you have U1, 2, 3, which takes X1 tensor X2 tensor X3 to X1 tensor X2 tensor X3. Okay. Then you can take the linear span of this, that you can extend it. That is just linear algebraic extension. But then there it will preserve the inner product. I mean, it will preserve the inner product here itself. Then now we have the lemma. If you have some operator which preserves the inner product on a total set, then it can be extended. That we have proved. So because of that, you get a unitary. Similarly, you have this is inner product preserving this map. X2 tensor X3 going through. Please go ahead. Okay. So this map is also inner product preserved. Okay. Then you know that then these two, whichever the way you go, this is associative in the sense. So what is associative here? U1, 2, 3 of X1 tensor X2. We know this X2 tensor X3 equal to, no, this is true for all of them. I mean, that is a property. That's what it's just here. So which is just U1, 2, 3 tensor X1 tensor X2 tensor X3 is equal to U1, 2, 3 X1 tensor. This is just elementary thing. I'm just stating that this is equal to X1 tensor X2 tensor X3. Okay. So in a sense, this is associated. You don't have to worry how you take. Okay. Because the associativity is preserved on the elementary tensor, so it will be preserved on the board. Okay, you don't have to worry. Okay, so this elementary, I mean, as I said, this tensor product is just that you have a Hilbert space where you have the elementary tensor, you can write it, and whose closure is that, whose linear span closure is that. So that is uniquely determined. Okay, it does associatively determined in this. Okay, you can take 2 at a time and then 1, or you can take 3 at a time or any number of them. It doesn't matter. How you do this, it doesn't matter. So that's what this is. Okay. This is just clear because of our proposition. Okay. There is a single unitary which just intertwine all these things. Okay. Now the proposition is the following. If you have Si contained in Hi, a total set, and His are Hilbert spaces, I equal to 1 to n, okay, Hilbert spaces. His are Hilbert spaces. Then all those Xi, X1 up to tensor Xn, where Xi is in Si, contained in H1 tensor to Hn, is total. Okay. Each Si is a total set. That is, you take the linear span and closure, that will be a total set. Then this is also a total set. And I think this is clear. Do I have to do this? Because it is just because tensor is some sort of continuous. So suppose proof, if you have some Xin, where should I should put the n is here, so I should use k or something. Xik, okay, converges to xi, okay, as k goes to infinity. Okay, I equal to 1 to n. Then x1 k tensor x2 k tensor xnk converges to x1 tensor. It is just the product is continuous. That's what I'm saying. That you can verify by for 2, for example. This converges to this as k going to infinity. You can verify this for 2 elements. Then it is clear. I mean, or you can use induction to prove it for n elements. So suppose some xn converges to x and yn converges to y. then I want to say that xn tensor yn converges to x tensor y. Then you can, generalize this proof for n elements. Okay. So this you want to, so what does this mean? This just means xn tensor yn minus x tensor y norm square. You want to compute this. So if you compute it, this is going to be norm xn times norm yn. I think there will be a square. This will be inner product of this with this, inner product of this with this, then the cross inner product will be there. Minus 2 real part of xn tensor yn, x tensor y. We have already expanded this inner product, okay, into norm of x square times norm of y square, right? This is what it will be. And as you can see, inner product is continuous because of this. So that is just going to be, you can replace this by 2 into inner product of xn x, y and y. Okay. Now the inner product is continuous and that will go to x norm x square. This will go to norm y square. And that will go to x. Norm is continuous and all that. So this will go to 0. Okay. So because of this, so 2 elements I have verified. Similarly, you can verify it for n elements. And so this tensor product. So because of this, if you can approximate in one entry by some sequence, okay. You can take the linear span of all these total set will be again. Again you can take the linear span in each of them. That will be the linear span of all this SI tensor, S1 tensor up to Sn, and you can take sequences from that, and it will be clear. Okay. So it is just clear. Okay, I don't want to write the whole thing as a proof. So if you have some total set, then the tensor product of those sets will be total then. So this will in particular imply corollary. So a separable Hilbert space means it has a countable dense subspace. Okay. Then if you take the countable tensor product of all those things, that will be a countable set. And if you take the linear span with rationals, rational complex entries with rationals, that will give a linear subspace, right? So which is a countable set again. Okay, these things implies that the tensor product, I want to leave it as exercise for you to think, but the proof is this, orally I'm saying. So if you take H1 up to Hn, which are all separable Hilbert space, that means they have a countable dense subset. Okay. So if you take the tensor product of those countable dense subset, that will be total there, which is again countable. Just the direct, which is just the direct product of those things. So, you just take the elementary tensor, that's fine. That is again countable. Okay. Now you take rational entries, rational linear span, that is countable, and that will be dense there. Okay. So tensor product of separable Hilbert space is separable. Okay. Okay. So next proposition is about orthonormal basis. Okay. So we have n Hilbert space. So each Hilbert space depend on I, J, Eij. J is in some something which should depend on I, Ji. Okay. Because it's ith Hilbert space, so the indexing set should be different. You can take it as natural number or something, but this works for any non-separable Hilbert space also. So let me write it like this. Okay. This is contained in Hi, is orthonormal basis. Okay. Eij, where I is fixed and J is varying. Okay. And this is the orthonormal basis for the Hi Hilbert space. Then this set Eij, where I is in I. I should be finite, no? So I equal to 1 to n. We haven't defined infinite. It's possible to define infinite tensor product also. I'll come to that the next proposition. Okay. I equal to 1 to n. And J is in Ji. Okay. Is O and B for the Hilbert's H equal to H1 tensor up to H. These are all very natural thing what you will expect. Okay, natural. So this follows because you compute the inner product first. Okay, you take any two things. This is, I mean, this is I is varying, J is also varying. So you take the inner product between Eij. Sorry, I have written, there is something wrong, right? This is not correct what I have written. Yeah, I have to write the tensor product, which I have written. So only when I write it, it's not correct. E, what is that I should have? 1 J is J1 or J1 or something. J1. Okay. E2 J2. Okay. Tensor up to E J E N J. Okay, where J I is in that J I. Okay, small J I is in J I. So this gives the, and this is Y and B. Sorry, this is Y and B for H1 tensor up to H2. Okay. So in particular, if it is finite dimensional, then the dimension is just the product of the, product of the individual dimension. Okay. So the proof, first you have to verify that this is an orthonormal set. So if you have E1 J1 tensor up to En Jn and E1 K1 tensor up to En Kn, then that is just going to be the product of I equal to 1 to n. Okay. E I J I, E I K I, whatever. Okay. That will depend. That is equal to product of the delta Ji Ki, right? I mean, that is equal only if the order tuple is equal. Okay? That is equal to one if Ji equal to Ki for all I, equal to 0 otherwise. Okay? So this is an orthonormal set. Okay, that is because it's just it breaks into product, so it's orthonormal set. And another thing we have to verify, for it to be an orthonormal basis, it has to be a total set. So that is we have proved already. So if we have a tensor product of total set, then if you form elementary tensor out of total set, then that is a total set. So we already proved, we have already noticed in the earlier proposition. Because of that, it follows. So from the earlier proposition, it follows that it's an orthonormal basis. Okay. Previous proposition, orthonormal basis. It is orthonormal, whatever it is. Okay. It is orthonormal. Anyway, this is an exercise in KRP's book. I don't know. This is not moving here. To share it again, or the screen is not moving here. Yeah.
So you take the lens, countable lens outside, take the lenses on that, and then you take the linear span in the rational.
Yes.
Do we actually need to scale it with the rational coefficient?
Yeah, otherwise it's uncountable. No? If you take the whole complex, you want a set.
Won't just the tensors which we take the dense, the elements from the dense subset, won't they also be dense?
No. Tensor product elementary, they will only give elementary tensor. You have to take the linear span of elementary tensor. That is what is dense there. You have to be always careful with tensor product. If you just make the product, that is just a set. That is not even a, that's not a vector space even. You have to take, if you take x1 tensor up to xn, if you have Hilbert spaces, h1 and h2, consider two Hilbert spaces at a time, h1 tensor, h2. Then if you take x tensor y, x coming from first Hilbert space, y coming from the second Hilbert space, x tensor y, that is just a set. All x tensor y. You have to take linear to make it a subspace. So that it is only that subspace is dense there, right? We have a set. A set need not be dense in some subspace, no? Right? You have to take the linear combination. So if you want some dense subset of a big space, if you close a set, you will get you don't. Why should it give the whole space?
No, I'm not saying it will get the whole space. It will be dense, maybe it will be dense.
No, if you take the closure, how will it give the whole space? That's what I'm saying. Why should it give? If you take the closure of that, does it give the whole space? If you take it dense subspace, you take the tensors. Okay. So why should it be dense there? That means at the most will give all the elementary tensors, right? It will only give all elementary tensors at the most. But you have to get the dense subspace somehow. Right? For that, you may need to. No, initial dense set need not be a subspace. You can have a set which is the whose closure is a space. That's right. But in this case, it need not happen. That's what I'm saying. Right? Shall I share it again? This is not. It's not coming here.
You have to share
Huh?
it.
You have to share it again. Yeah, what is getting shared? Oh, I have shared something else. Okay. Okay. Okay, so this is okay. Okay. Now let us talk about what is called infinite tensor function. Okay. So this is just a construction. So let me just give a construction. So this is basically, you can call it definition. Okay. Definition. So let Hn n equal to 1 to infinity be a sequence of Hilbert space. Have a sequence of Hilbert space. So to construct infinite tensor product, you need what is called a stabilizing sequence. You can't directly do that. Direct sum you can do. Okay, if you have countably many Hilbert space, you can take the direct sum. Sum is not the problem. But even that we haven't defined. We will come to that. Did we define in that class? I don't remember. Anyway, I will define it again because we are going to take infinite direct sum. So I will define it. So if you have a sequence of Hilbert space like this to construct the tensor product, countable tensor product, we need to have what is called stabilizing sequence. So let phi n and Hn be such that be a unit vector. Norm phi n equal to 1 for all n. Okay. So then this phi n is what is called a stabilizing sequence. You can take any stabilizing sequence, okay, and construct the Hilbert space, and there will be a unitary between them. But then, if you want to do some work with some Hilbert space, then the unitary may not behave nicely. When you want to do some other construction, you have to always make sure the associativity with that. Phi n is what is called stabilizing sequence. It is just a sequence of unit vectors you are taking in each Hn. That's all. Okay. This is just called stabilizing sequence. Sequence. Okay, then you take the set S, which is equal to all those set U1, U2, like this. You take the direct product, infinite direct product like this. Un n equal to 1 to infinity, and Un is in Hn, and Un is equal to phi n after some time, after finitely many of them. Pn. Un is equal to Pn except for finitely many. That is, after some time, it becomes Pn. It's just, that is our stabilizing. It stabilizes to Pn. Okay, that is why it's called stabilizing sequence. Okay. Now it's so in anything you will have UNs which are only finitely many. Okay. So you can define K of any K of any UN and Vn. You can take any sequence like this to be the product. Inner product UN. So only finitely many of them will survive. After that, it's one everywhere. Okay. I mean, it's because it's a product, we need one to stabilize it. Okay, it will be one after. Okay, after some time. So this is a finite product. Okay, so this is well defined. And this is a positive definite kernel. On yes. So that is just you have to verify, like you have verified already for Hilbert space and everything, it's the same thing. I mean, let me not write all those things. The positive definite kernel, what you have to do, you have to verify this product, summation alpha k prime, alpha I or alpha j, and k of xi, xj is positive for all of them, right? So if you use that, this is inner product. If you just use that, that will be this will become something like summation alpha I xi alpha I. I mean, it will be just some inner product you will get. So inner product of same thing is always positive, and because of that, it's positive definite kernel, which you can verify. Okay. So I leave it this as an exercise. You better write it and then verify yourself. Okay. And yes, S crosses. S crosses is yes, doesn't matter. As a function, it's a function defined on S classes. We say it's a kernel on S. Usually we say it's a kernel on S. Okay. I mean, if you have a set X, then the kernel is defined on X cross X or something, so that we integrate it or sum it to get something. That's what we usually call it as a kernel. Okay. So now you define now H is a new Hilbert space. H be the whatever we call as Kolmogorov dilation or Gelfand pair. Which I call it as Gelfand pair. H, and I mean pair means you have a function also. You have a function which I denoted by V, I think. Okay, H will be the Gelfand pair associated with this Hn. I mean, sorry, with this S, whatever that's it, yes. Yes and K. Okay. What does it mean? It is H is a Hilbert space. V is a function from S to H, and V of that S is dense. Is total, sorry, is total. Linear span of that is everything. So that is what the Gelfand pair says. And V of any, so as you know, S is something almost direct product which stabilizes after some time using that Pn. Okay. So V of any U1, U2, if you have something UN, after that Pn plus 1, Pn plus 2, like this. It goes like this. So which you can denote it as U1 tensor U2 tensor up to UN. Then if you wish, you can take it as Pn plus 1 kind of thing. Or you can just leave it finitely many of them. That doesn't matter. You can just take it to be, you can just write it like this. Doesn't matter. Okay. So you can make finite tensors on that. So this is this H is what is called the infinite tensor product of that. H we can define it to be Hn infinite tensor product n equal to 1 to infinity. Okay. And we have to remember this Phi. It depends on the stabilizing sequence Phi. Okay, Hn Phi. So this is what is the infinite tensor product. And there these finite tensors are, you are only taking finite tensors. You can actually form infinite tensor, but not everything will form infinite tensor. There will be some condition.
Can you repeat the response of that V of X?
No, our construction is if we are given a set S, and if you have a positive definite kernel, then we can form a Hilbert space H, where there will be a function from this total set S to H, where this range of this S will be total there. That's all. So the S is all those tuple U1 up to UN, and after some time Pn, it's just the stabilizing sequence Pn. Those we are calling it as elementary tensors. Those that image we call it as elementary tensor. That's what it did for finite tensor also. Okay. So here this is what is infinite tensor. And so here the finite tensors are the total there. Okay. The remark I want to take, you actually can form infinite tensor for some particular sequence, not for every sequence. It has to satisfy some square summable condition. Okay. I mean, I'm not getting into it. Not all of them you can do it. Okay. Under some condition, you can indeed define some infinite tensor for some element, some sequence of elements. Okay. So this is what is infinite tensor. Okay. So if we may not be using this in this course, maybe not in the next course also, I don't know, because we will be dealing with finite tensor all the time. But there are situations where this is used. This is very used. Okay. So, okay, this is about infinite tensor. Okay. Then the next thing is, this is what is important. What I'm going to do now is what is important. This is what is called, already I have defined this, symmetric tensor and anti-symmetric tensors. Tensor product and anti-symmetric tensors. My problem is I tend to write fast. That is why my handwriting is not good. But if I write slow, then I'm not able to write it. I forget what I want to write. Okay. Symmetric tensor product and anti-symmetric tensor product. So this is about symmetric. So when you use this, this is about the same Hilbert space. You can't take different Hilbert space and do this. Okay. So HB1 Hilbert space, a fixed Hilbert space. Okay. Then Sn be the symmetric group of permutation group. Okay. Permutation group of n elements. Okay. n elements. Okay. Then for sigma in Sn, I have already defined it and just redefining it again. Sigma in Sn, you define U sigma from H tensor up to H n times. You take the same Hilbert space. Okay. Right? You take an x1 tensor up to xn goes to x sigma inverse 1. I take inverse because I want it to be a representation of the symmetric group. Okay. X sigma inverse n. Okay. You can put sigma also. That doesn't matter. I mean, if sigma is a permutation, sigma inverse also. Then U sigma extends to an unitary. I mean, this is defined on elementary tensors. I have mentioned last time itself. This preserves inner product. If you take x1 up to xn, y1 up to yn, then that will go to x sigma inverse 1 up to x sigma inverse n. You take the product, inner product, it will be just the product is permuted among themselves, which is same, of course. If you have a product of n numbers, you permute it among themselves because it's commutative. So complex numbers is commutative. So because of that, it is just the product is same. So it preserves the inner product. So when an operator preserves, even if you have a function which preserves the inner product on a total set, then you can extend to a unitary. Extends to a unitary operator on H. Okay. So U sigma is in unitary. Okay. Now, I mean that H tensor H, I also sometimes write it as nth power, H tensor n. I put it like that also. Okay. So here I want to write, I put an S. Okay. Sn equal to all those maybe xi in Hn, the tensor, such that U sigma xi equal to xi for all sigma in S. maybe I should say something here, which I write it here. U sigma prime is equal to U sigma prime. You can verify that, okay? I mean, it is just clear. That is why I put an inverse. Just think about it. So this gives a representation of the SN permutation group, and elements fixed by all U sigma, where sigma comes from the symmetric group. That is, this is what is called a symmetric. This will be a, you can prove that this is a Hilbert space because this is all fixed by, I mean, this is a linear space. If something is fixed, scalar multiple of that is fixed, sum is fixed, psi1, psi2, sum is fixed, it's a vector space. And U sigma is an operator, continuous operator. So it will fix the limit also. So this is a subspace, closed subspace. So this is a Hilbert space, and this is what is called symmetric Hilbert space, symmetric tensor. This is a Hilbert space. Okay. There is something called so this is the symmetric tensor, which I have defined in the last class. There is something called antisymmetric tensor. Sorry. That is all those xi in H tensor n such that U sigma xi equal to, you take the signature of that. Signature, what is signature? What is the notation? Is this okay? Epsilon by xi. Signature is, if it's an odd permutation, E sigma is where E sigma equal to 1 if sigma is even permutation, equal to -1 if sigma is odd permutation. Okay. So if it preserves up to that sign, up to that sign of the permutation, okay, then that is what is called antisymmetric tensor. Okay. This is what is called antisymmetric tensor. Tensor product. Okay. Oh, I forgot something about tensor product. I have to say that the operators, you can define operators of tensor product, so which we'll do it now. Before getting into the next turn, we'll do this. I forgot to prove something. Anyway, this is where we have defined symmetric tensor and antisymmetric tensor. We'll come back to this again. Okay. So if you have written it, I will go to the next one. This is the proposition. Tensor product of operators I want to do. Okay. Forgot. So if you have H1 to Hn, Hilbert spaces, okay, then H is equal to H1 tensor up to Hn. And if you have a Ti is an operator on B of Hi, okay, then there exists T, which is equal to, which we also denoted by T1 up to tensor Tn, where T of any elementary tensors equal to T1 x1 tensor Tn. Okay. This is true for all x1. So you can define like this. You have a linear operator on each Hi. Then you can define on elementary tensors like this. Then you extend, there exists a unique T. Then you can extend it linearly to the linear span. You have to show it's bounded there. Once it is bounded, you can extend to the whole vertex. So the only part which is we have to prove is it extends. I mean, it extends to the linear span. On the linear span, it is bounded. You can define on the linear span, it is bounded there. Further, norm T is equal to the product. So this is important. We have already defined it for finite dimensional. We have defined it like this and extend. There we did not worry about boundedness. So we just defined it like that. I don't think we computed the norm. which we will do now.
Is it in the definition, this norm thing?
No, further it follows.
It follows.
I mean, that is also not definition. There exists a unit T such that T satisfies this. So once T satisfies it, that is unique. It's clear. This will be the only operator. That is part of definition and part of uniqueness. Everything is clear. All you have to show that extends to a bounded operator. That's what you have to show in that. Then it follows that this is also the norm is the product of them. First, we will verify for a let Ti be I equal to 1 n or self-adjoint and Hi are finite dimension. Let's first assume this. There we verify this. Then we can extend it. Then we can prove it for any Hilbert space. Okay. Okay. So Ti is a self-adjoint. Okay. So there exists Ei1 up to Ei Ni, okay, contained in Hi, orthonormal basis, finitely many of them. And this is a self-adjoint operator. So it's diagonalizable and there exists eigenvalues and eigenvectors for that. That's what I'm writing. I1 up to Ei Ni, sorry, this is lambda. Values for Ti. Okay. So I'm just taking Ei1 up to Ei because the n dimension also may vary. Okay. Because we are assuming finite dimension. There's an orthonormal basis and which is also eigenvectors for those Ti's. Okay. And lambda I1 up to lambda n is an eigenvalues of that. Okay. Okay. Then we can define define T equal to T1 tensor to Tn, which is defined. We know that then the direct product of the orthonormal basis and orthonormal basis for the tensor product. So we define T acting on E1 I1, V1 I1, right? I1 tensor. Okay, this is okay. You understand. I mean, there is some confusion about the notation, but it's okay what it means. 2I2 tensor up to Nin. Okay, is equal to lambda I I1 and lambda I1 lambda I1 I correct. I mean, you just have the I. Oh, no, wait a minute. Whatever. Let me write it in form before. What is it? So you can just directly write the tensor product. No, so okay. Tensor product of Ei Ik, Ij, Ik. Okay, Ik. Okay, Eik. I equal to 1 to n. Okay, this k is the only thing. Ik. But k will depend on, I know, each I you can take a different k. So Tki. Ith thing and the Ki, you choose one of them among the orthonormal basis. Ki, T acting on this. This is equal to some. Okay, I put the inside that. You can take the lambda out if you want. Okay, lambda I Ki acting on Eik. Okay, you put the corresponding eigenvalue on the corresponding eigenvector. Okay, take the product. Okay. Then you define this operator. This is finite dimensional. You defined it on the orthonormal basis, so you can always extend it. There is no problem. Okay. Now, what is this norm of T? So T is an operator with the T is again self-adjoint because all its eigenvalues are self-adjoint. Product of reals are reals. So T is self-adjoint operator. T is self-adjoint because all its eigenvalues are product of those individual eigenvalues, and which are real, so they should be real. So T is self-adjoint. Eigenvalue is some self-adjoint operator or something whose eigenvalues are real. Okay, so T is self-adjoint with eigenvalues with eigenvalues lambda, the product, right? With the lambda product pi I equal to 1 to n lambda I ki. Okay, lambda I ki, and eigenvectors tensor I equal to 1 to n e I ki. This is for a particular pair of ki. Okay, I mean this here the k1 up to kn you have to fix, then you will get a vector. You have to take the product is formed through I, and k1 up to kn you have to fix, that will give one vector. That is in the direct product of this set. Okay, that will give one vector. So this is corresponding eigenvalues and eigenvectors for that. Okay, then what is the norm of T? So if you have an I, so you know this, if you have a self-adjoint operator with eigenvalues lambda 1 up to lambda n, then its norm is maximum of the eigenvalues. Do you know this? You can always verify. So this is very easy. I mean, I will write it in the arrays. If you have some operator T of ei equal to lambda I ei, okay, then you know that norm T. But so this means that norm of any Ti summation some you have to alpha ei. This is going to be summation alpha I lambda I ei. Okay, you take the norm, you take the norm, you take the norm, you take the norm, which is less than or equal to, you can take the mod lambda I out. Summation alpha I ei you will get summation alpha I ei. Okay, this will imply that norm T is less than or equal to norm lambda I. Maximum of, sorry, you can take the maximum of lambda I out. So this will imply that norm T is less than or equal to maximum I mod lambda I. Okay. On the other hand, lambda on some unit vector ei, the lambda is attained. So this should be the norm. Okay, so it is clear. So this proof you should remember all the time. I mean, you need not. This is how you always compute the norm. You first say that the norm is less than or equal to something, then you say it's attained. Either is attained directly or there's a sequence where it will be attained as a limit. Okay, so norm T is equal to, here it's finite still, it's a product and finite still. So this is equal to maximum of K, Ki1, K1 up to Kn in all those things. And the product of I equal to 1 to n, lambda mod of this, lambda I Ki, okay, mod of this. This will be the norm of T. Okay, and that is equal to, you can take the maximum inside each maximum because it's a finite product. No? You can take the maximum of this, right, which is equal to pi of I equal to 1 to n maximum over this ki. I mean, over this ki, where ki is follow mod of lambda I k. And that is exactly equal to I equal to 1 to n norm of T. Okay? That is just the product. Okay, think about it. So this says that for finite dimensional, you can define the tensor product directly, okay, which we have already defined. Then for self-adjoint operator, norm T equal to the product of the norms. So this we have proved for finite dimensional Hilbert spaces. Now we want to do it for infinite dimensional Hilbert space. Of course, for any operator, not just for self-adjoint operator. So for that, let's do
the operator also assuming the self-adjoint.
Correct. No, for that, yeah. Using eigenvalues, I define, but you can anyway define. That is not the point. I mean, here I want to compute the norm. That's why I use eigenvalues. Otherwise, it's not needed. In finite dimension, we can anyway define. Okay. For infinite dimension, we have to show its bound. Okay. Now let H1, H2 be arbitrary Hilbert spaces. Maybe I should have written it as a lemma, but finite dimensional case it will follow. The arbitrary Hilbert spaces. Okay. And Ti is in P of Hi. Okay. Then we can define T x1 to xm by Ex1, so Tix1, T1 x1 tensor T2x2 tensor to Tn xn. Okay. Tn xn. You can write the tensor product like this and extend linearly. Extend to linear span. Extend to the linear span of elementary tensors. Okay. Okay. Now we want to say that on the linear span it is bounded. For that, we have to worry about this. Summation T of summation alpha j. Okay. This is some linear alpha j scalars. Say in C. Okay, some scalars. And some j varies from some k, 1 to k, j equal to 1 to k or something. Okay. J equal to 1 to k. And here we have elementary tensors. So the elementary tensors are we have to have different things, no, depending upon j. So x1j tensor x2j to xj. Right? Correct? Okay. Now square, we always, because we want to take inner product. Okay. I mean, the norm, we can't work with norm. So we have to take inner product. Okay. So that is equal to, you take the inner product basically. So this is equal to summation. Move it here. Alpha j bar. Remember that our inner product is conjugate linear in the first variable, alpha k. Okay. Where j and k varies from up to k. So j, oh, I already have a k here. So j prime. J prime. Okay. J prime varies from 1 to k. Okay. Alpha j prime. So here I will have alpha j x1j tensor up to, maybe I will write it as a this kind of tensor. Tensor I equal to 1 to x j I. Okay. And alpha k, alpha j prime. Alpha j prime tensor I equal to 1 to n.
Already taken the RCC as a
I mean, so I have swallowed one step. This will be inner product of this times inner product of the same thing. And there is a summation which you can take it out. That is how we are defining the T. You take the summation which take it out. And there are two summation in the inner product.
So within the inner product, there shouldn't be any alpha.
Sure. That is right. You are right. Correct. Okay. Okay, that's right. So now we have T here, right? Now we have
BTO.
yeah, correct. Now I want to use the previous one now. So I want to write it in the right form. So I mean, it will be T there, that's right. But that's what we want, we are verifying. This is equal to, I just put the T here. I mean, the tensor T. Okay. Yeah, I will have T here. I have Ti here. Ti here. And then Ti of x j prime, right? Okay, this is okay. So now point is this. I can take this Ti, I mean that this will be the product. I can take this Ti the other side, j equal to 1 to k, alpha j bar, alpha j prime. Maybe there is a pi, I equal to 1 to n. Okay. X ji t star t. The t I can take it to the other side as t star t. Okay. Acting on this x j prime I. Okay. And if you want, you can put a, I mean, TI star TI. TI star TI. The point is now, I mean, we are using some J1 up to Jn. I mean, J, you are fixing an I. On that, you have a J varies from 1 to N. Okay. So what I do is the following. So that is what will, I mean, here all this X, so if you have this set, okay, let Pi be a projection from Hi to X, I is fixed. So J is first, no, J1 up to, no, I is fixed. So 1J. 1I, X2I, up to Xki. I mean this, yeah. Okay. Okay, you have finitely many of them. So this is a projection onto the span of this. This is just finitely many. You don't have to close it. You don't have to close it. You just take the span. Because finitely many of them. So it's a finite dimensional space. Okay. You take this projection. Okay.
Should there be
X Xja or Ij, which one I used? 1J, 2J. So Xij. Yeah. I have interchanged here also. I'm interchanged here. Xij, Xij, and here also. Xij, Xij. Okay. Ij prime, Ij, Ij prime. These are all some notation. So it should be I1 up to Ik. Okay. So this is a finite dimensional, the finite rank projection. The range of Pi is finite dimensional. So I can insert this Pi on the other on that side. Okay, if you have Pi to be like that, then this is equal to summation J prime equal to 1 to K alpha J bar alpha J prime pi of I equal to 1 to N. Okay, Xij Pi Ti star Ti again Pi. Okay. You can put a Pi. Pi is the projection.
Okay.
Okay, you apply Pi here if you want, then you can bring the Pi to the other side. Okay, if you want Pi of Xij prime. These are all in the range of the projection, so you can put a insert a Pi. Doesn't matter. You can bring the Pi other side. Okay, so this is I mean, anyway, I have unnecessarily taken the whole thing. So this is same as summation alpha I, alpha j. Okay, alpha j of tensor product of I equal to 1 to N. I need not have taken the summation outside, but that doesn't matter now. Xij, okay, Pi, Ti star Ti, Pi, acting on tensor product, I mean, tensor product of this. There is a summation also. Summation alpha j prime, okay, then Pi, Ti star Ti, Pi, okay, acting on Xij prime, tensor product of I equal to 1 to N. J prime. Okay. Thing is, these are finite dimensional operators, and this is self-adjoint operators. This Pi, Ti star Ti, Pi is self-adjoint, it's finite dimensional operator. Okay, and this is all happening inside a finite dimensional vector space. So you can use the thing before. So that will imply this is equal to norm of this P of Ti star Ti, Pi. Norm, we can take norm of this times, then you will be left with that only. That is just summation alpha j Xij norm square. I mean, summation X T X is less than or equal to norm T times norm X square. Okay. So because of that, this is true. And this is less than or equal, sorry, there is a product. Product I of I equal to 1 to N. This is less than or equal to, these are all positive numbers. So I equal to 1 to n norm ti times summation alpha j xi j. Okay. So we started with some linear combination of the elementary tensors. Then we got this inequality summation ti times this. These things will imply whatever the operator we have defined on the dense subspace, not on the whole subspace, norm of t defined on dense subspace. Dense subspace spanned by elementary tensors. Okay. I'm writing too many things. Elementary tensors. Okay. That is less than or equal to I equal to 1 to n norm ti. That's what we have proved. Okay. No, not ti square. Sorry, this will be ti star ti, which is equal to ti square. Sorry, here it should be square. And because of the square, it will become norm ti. That is ti star ti. You will get right here. We have pi, ti star, ti, pi. Pi is norm less than or equal to 1. Is a projection. I mean, norm equal to 1 in fact. So if you have, I mean, you know this inequality, norm of ts is less than or equal to norm t times norm s. Okay. Because of this, you can take this out because it's less than or equal to 1. So this is less than or equal to norm ti star, pi, which is norm t star. We have proved that norm t star or t star t is equal to norm, which we call the C star identity. So because of that, we get norm t square and we get this. So we have proved that norm t is less than or equal to, so this is a bounded operator. Okay, and I mean, this is a bounded operator, so t can be extended. So t can be extended to the Hilbert space, tensor product of I equal to 1 to n h. Now, we have only proved that is less than or equal to ti. We have to show that the norm is attained or it can be approximated for any given epsilon. Now, for epsilon greater than 0, choose xi in hi such that norm of txi, ti xi is greater than or equal to norm ti minus epsilon, which is always possible. Norm t and norm xi and norm xi is equal to 1. Okay. That's the definition of norm. Norm is supremum of all those, I mean, norm tx, where norm x is less than or equal to 1 or equal to 1. Huh? Simple. Using the finite dimension, we proved that this is less than or equal to this. Okay. Then I want to prove it's equal. For that, I given epsilon, I choose norm xi like this. Okay. Now let x equal to x1 tensor up to xn. Okay. Now tx is equal to t1 x1 tensor up to tn xn. Okay. Norm of this, norm of this, norm of this, norm of this. And norm x is equal to, they are all unit vectors, so that should be also equal to 1. Norm should be equal to 1. Norm tx equal to this. And this is equal to norm of ti xi, the product. Okay. And this is greater than or equal to norm. Oh, maybe I put an epsilon. I mean, I can use epsilon in whichever the way. Epsilon times some number is also epsilon. So, okay, put it like this. So this is greater than or equal to 1 minus epsilon power n norm I equal to 1 to n norm t. Okay, take epsilon going to 0. This is true for all epsilon. Okay, by taking epsilon equal to 0, this implies norm t is greater than or equal to norm. We have already proved the other inequality, so they are equal. So this I should have done before introducing symmetric tensor product, but that is done now. Yeah, I started late, but doesn't matter. We'll start now. Okay. So I'll stop recording and then we'll discuss other things.